Good morning, my dear students. So today I'm going to teach the practical explanation or the applicability of the settling velocity which we derive in the third class. So today is the fourth video. So to begin with the application of sedimentation, let me introduce you a small theory. Let's say this is a jar, okay? This is like a sedimentation tank. A particle is over here on the top. This particle is going to settle at the bottom. So this position is nothing, it is the settling. Our objective is to make this particle settle at the bottom, okay? This depth is jet node. The depth is jet node. And let's assume that the settling velocity of this particle is V node. Settling velocity, okay, of this particle 1 is V node. Now what happens is, the time taken for this particle to reach over here, I mean, if you want to make this particle settle down here and it comes down here, this is called settling or sedimentation. What we can say is, its settling velocity is equal to jet node divided by time node. T node is the time. T node is the time taken to settle at the bottom, time taken to reach the bottom, okay? Fine. This is just a universal concept. So the time taken can be calculated as the jet node divided by V node, number 1. Okay, now, if you try to make a sedimentation in a chamber, it is not always all the particles are of same size. Some particle may be heavier, some particle may be lighter. Okay, I'll give another example. If you happen to see another particle over here, huge, very, very big. This one is bigger, so the settling velocity of this will be again larger. Because as per the Stokes law or as per the terminal velocity formula, settling velocity is proportional to d, correct? In laminar's flow, it is proportional to d square. Higher is the diameter, higher will be the settling velocity. So this particle will settle at the bottom before t naught, right? If t naught is say 5 minutes, this particle may settle at the bottom by 2 minutes or 3 minutes. So we don't have to get a headache of bigger particles. It will settle down. Clear? Now the problem is, the particle that is present in the water or the wastewater, it is not bigger. It is, some are smaller also. Some are smaller, maybe I'll say another one, a small one. If this particle comes down, since the diameter is smaller, the settling velocity will be less than V naught. Right? If the settling velocity is less than V naught, then the time taken will be more time will be taken. This is small, this is constant, so this will be more, right? So that means the time taken will be less than T naught. Another example I'll give you. Say for the larger particle, the time taken T will be less than T naught. But for the smaller particle, the T will be greater than T naught. Am I correct? The larger particle will take very less time, but the smaller particle will take more time to settle at the bottom, right? But when we design a water treatment plant, we always design for a typical particular size. For a particular size, we will have a settling velocity. We will design only for one settling velocity. We cannot design for so many particles. Okay. So our ultimate aim is, in case if there is any smaller particle, what will be the removal? That is our objective. If this particle is there, then removal is equal to what? This question is going to come. Now, in continuation with it, let me say another particle is there over here. Fine. This particle here, this depth is Zp, and its settling velocity is Vp. Okay. So what happened is, and this is number one, and number two, let's say this particle reaches over here by T naught, this particle also reaches here in T naughts. In the other example, here T is equal to T naught. I am taking this T naught. Same time means both the particles settle down at the same time. So can I write like this? T naught is equal to Zp by Vp. Number two. Okay. So both the particles settles down, and this one is Vp. Sorry. This one is particle P. So both the particles settles down at the same time. Therefore, T naught is equal to Z naught by V naught, and T naught also Z by Vp. From 1 and 2, what we can conclude is Z naught by V naught is equal to Zp by Vp. Implies to Vp by V naught is equal to Zp by Z naught. This question is very important. Okay. Now, from this observation, what I'm going to conclude is, if there are particles smaller than the diameters, what will happen is, they will remove not completely, but they will be removed in fraction. If dia particle is less than this first one, D1, okay, this is D mu. If this is less than this D1, then removal will be, it will remove in fraction, not completely. But if D mu is greater than or equal to D1, just like what I said, if this diameter nu is equal to this diameter or more, settling velocity will be more. So definitely it will be 100% settling. Am I correct? So I repeat it. See here again. This is our observatory particles. But if the particle is bigger than this particle, settling velocity will be very high, and then it will be completely removed. So if the diameter is equal to or greater, it will be 100% settling. But if the particle is very small, it may not be able to reach at the bottom. So what will happen is, the removal will be fraction. Okay. And what is the removal fraction? The removal fraction is in the ratio of settling velocity of the particle to the settling velocity of the design velocity. V naught is nothing, it is a design settling velocity. Is that clear? Fine. Now let me repeat it again. If the particle is bigger than the design particles, our observatory, then settling will be completely 100%, because settling velocity will be high. But if it is small, the settling will be in the fraction of settling velocity of the particle to the settling velocity of the design or our observatory value, or it is in the ratio of different depth. This is just for evaluation. Okay, fine. Have a look. If you have any doubt, I'll give you the class note and you can still ask me in your Google Classroom. I'm going to solve that problem right now based on this. Is that okay? Let me drop it off. I'm going to do a numerical. Now, let me do a numerical, okay? So, let's say this is a chamber. You want to design a water treatment plant or a wastewater treatment plant. So first thing what you do is you check what is the water. In this water, when you check, you find that this water contains a lot of different particles. Maybe larger size, smaller size, smaller size, medium size, very huge size. So there are different sizes of particles. The water that is coming from a canal or maybe from a river that you want to treat, it won't contain only one particular size of 0.2 mm or 0.5 mm. It will contain different size. Is that clear? So before designing, we have done some observation. There is some equipment that is not need to mention, but it is called, say, particle size distribution. This is the name of an equipment. By using this equipment, we will put an X-ray on this, and then we will see what different sizes of particles are present. Okay. So based on this calculation, what we find is, number one, the size, say 0.1 mm. Okay, this one I'm doing it. This 0.1 mm and contains 10%. Okay, this is quantity. So the total solid present over here, 10% is 0.1 mm. Am I clear? And then 0.2 mm, define it 20%. And then similarly, 0.3 mm, define 15%. 0.4 mm, 5%. 0.5 mm, then 30%, and then 0.6 mm, they got, say, 10, 20 is 30, 45, 50, 60, 70, 80, remaining 20% is 60 mm, sorry, 0.6 mm. So this sort of sample, we collected it and we came to see that different sizes are there, not only one size. So this is 10%, 20, 15, 5, 30, 20. I think it's very clear. Okay, now by using the last class, what you can do is you have to find the settling velocity of all these particles. Last class, we have done settling velocity of 0.5 mm something. So by using this diameter size, we can find the settling velocity of the particle using terminal velocity or Stokes law. The finding of settling velocity from this size itself is a question of 30 marks. But here they have given it. Okay, the settling velocity is in terms of millimeter per second, and it is 0.2, 0.25, 0.3, 0.35, 0.4, and then 0.5. Okay, this is the question given. Let me explain once more again. A sample is there from the river. The particle contains are of different size from 0.1 to 0.6 mm. And all these particles, when we analyze, we find that 0.1 mm contains 10%, 0.2 mm contains 20%, likewise 0.6 mm contains 20%. So all over it is 100% solids. Clear? And then the question itself, they have estimated the settling velocity. For 0.1 mm, settling velocity is 0.2. Mind you, this itself, solving, this is another 30 marks. Last class we have done it. Similarly, for 0.2, they find it to be settling velocity is 0.25. Likewise, for 0.6 mm, the settling velocity is 0.5. So what we can see here is, with the increase in the diameter, the settling velocity also increased. Clear? Now, the question is, they said that already they have a water treatment plant or they have a grid chamber. They have a grid chamber. Okay. And what they said is, they have designed this grid chamber. How to design a grid chamber, I have not taught you till now. But let's do it in such a way that before designing, let's try to evaluate the performance of an existing grid chamber. Already a building is there. Let's try to analyze how this building is constructed before we know how to design a building. Okay. Similarly, this grid chamber, they design by using a particular settling velocity. I explained you. So they said that this design settling velocity is equal to 0.35 mm per second. Okay, that means this part, this part. Okay. Now, what they said is, if I have a grid chamber which is designed by using this value for this incoming water, what will be the performance of the plant? Example is, this is your grid chamber. The water is coming like this, it is going out here, and all the particles are settling down. This grid chamber is designed with 0.35 mm per second. But the incoming water is having this property. So what will be the renewable percentage? That is the question. Is it clear? Fine. This is just a picture I'm showing you. Okay. Now write the question, see the question properly, and let us solve it out. Okay. Fine. Let me tell you here. I'm not solving the answer right now. Here, this is a design settling velocity, and this I will say is D0. That means this is D0. Number one, any particle with D1 greater than or equal to D0. If any particle is there greater than this particle size settling velocity, that means the settling velocity will be more, it will be heavy, so it will be completely settled. Okay, so this is 100% renewable. Do you agree with me? That means 0.35 mm is our design value. That means the size particle is 0.4 mm. So any particle which may be equal to 0.4 mm or more than 0.4 mm or having settling velocity of 0.35 mm per second or more than 0.35 mm per second, they will be definitely heavier and they will be settled down completely 100%. Fine. Number one statement. Number two statement is, any particle D2 which is smaller than the D0, that is, those particles means this side, okay, this radius. this side. This particle will not be settled completely. They will be settled only in fractions. It is fractional removal. Fractional removal. And the value will be, I told you already, settling velocity of the particle divided settling velocity of the target value. This V0 is nothing. This is our 0.35 mm per second. See properly? I'm going to replicate everything right now. So over here, we have two parts. The first part is particle size equal to or greater than this side. This will be 100% removed. Or on the smaller side, they will be removed in a fraction, and the formula is Vp by V0. Whereas our V0 is 0.35 mm per second. Is that clear? Okay. Now let me run it off. If you want to see again, you can pause the YouTube and you can see. Okay. Let me continue. Now, removal is equal to, I told you, that is R1 plus R2. R1 is greater than or equal to D0 plus R2 is less than D0. Okay, diameter, this diameter. So this is 100% removal, and this is fractional removal. Okay, so in 100% removal, these are what? These are 0.35 mm size, am I correct? Oh, sorry. 0.4 mm size plus 0.5 mm size plus 0.6 mm size. Fractional removal is 0.1 plus 0.2 plus 0.3, I think. Okay. This is fractional. I'm not saying that you have to plus this value. Okay. Now what happened is, for 0.4 mm size, what is the percentage removal? It is 5% plus 13% plus 20% is equal to 55%. Okay. That means since 55% of the incoming solids are higher than the design value, this 55% solids will be completely removed. And this 55% comprises solids of 0.4 mm size, 0.5 mm size, and 0.6 mm size. Is that clear? However, for these particles smaller size, they will be removed in fraction. The removal in fraction will be Vp by V0. 0.1 plus Vp by V0 of 0.2 plus Vp by V0 of 0.3. Is that clear? I think it's very clear. Fine. Now this part is done. Let me evaluate this part. This part is for settling velocity of 0.1 mm. It is, what is the settling velocity? As per the question, it is 0.2 mm per second divided by 0.35. Am I correct? And that means the ratio of settling velocity of the particle to the designed settling velocity into how many percentage it is removed? It is removed 10%. 10%. Plus the settling velocity of 0.2 mm is 0.25 divided by same V0, 0.35. How many percentage of 0.2 mm is there? There is 20%. Plus settling velocity of 0.3 mm is 0.3. Settling velocity is 0.3 divided by 0.35 into how many percentage? It is 15%. Okay. Now you see here, for the 0.1 mm, the fractional removal will be this much. Settling velocity of the particle divided by the initial velocity or design velocity into how many percentage of the particle? 10%. Similarly, settling velocity 0.25 divided by 0.35 design value into 20% incoming. Settling velocity 0.3 by 0.35 into 15%. Okay. So then the upper part. So R is equal to 55% plus, how much is this? This is 0.1 is, this is 0.857 into 15 by 100. This part plus 0.25 divided by 0.35 into 20 is 0.7142 into, this is 20%, 20 by 100 plus 0.3 by 0.35 is 0.5714 into final is 15%. No, into 10. 15, 20, 10. Okay. So this is equal to 55% plus 32.8%. This from here to here, it is this value. Okay, so this is 87.8%. I think the concept is clear now. Okay, so 55% is completely settling down, which are the particles which is equal to or heavier than the design value of 0.35 mm, and then these are the smaller size particles which is removing friction. Is that okay? So this total is 55 plus 32, 87.8%. So the final question is, if a grid chamber has already been designed with settling velocity of 0.35 mm per second with the characteristic of the incoming water as given in the question, then those particles, the removal will be 87.8%. Is it clear? So from here, another observation one we can say is, let it be any grid chamber existing in your village or in town or in your city, and from their engineer you ask what is the design criteria of this grid chamber. They must have some paper, they may not be knowing also, and you know that the design criteria is settling velocity is this value. On a particular rainy day, it's a lot of rains, kafi barish. So you collect the samples because it will contain a lot of surface runoff and sediments. You collect the sediments, you put in the particle size analyzer, not in the cell, maybe in chemistry or physics lab, see the distribution of the particles. And then you can estimate that with the desired settling velocity, with the different size of particles on a rainy day, how much sediment will be removed in a grid chamber, how many will be escaped out. So performance won't be consistent all the time, it will be fluctuated. But our target will be always around 70 to 90%. That's the end of this class. By the next class, I'll be reading some graph papers. So mind you, while copying the next class in the YouTube, you try to have a graph paper with you and I'll continue with it. Okay? So for any doubts and discussion, we'll try to adjust a day and we'll meet everyone in the Google Meet. And for all the assignments you submit through Google Meet, I'll give you the space. Okay? Just wait. Before finishing, the cycling velocity. Sometimes in some other books, this cycling velocity is nothing, depth by time. In some other book, what happened is, you will call it, last semester I told you, surface overflow rate. Surface overflow rate is nothing, how much water discharges per unit area. The unit is meter cube per day per unit area, right? In other way, if you cut it, you will get this as meter per day. This is same as the settling velocity. So I can say settling velocity and surface overflow rate are same, but I won't say it is not exactly the same. It is as per the application. So the unit should be as it is. How much meter cube of water has been flown per unit area in a unit time. Okay. So, but literal meaning, it has the same unit. So sometimes when they ask the question, they will say design settling velocity, or sometimes they will say design SOR, or sometimes overflow rate. I mean to say it has the same meaning. Is that clear? In the previous question also, rather than saying settling velocity, they may say the overflow rate is 0.2 mm per second. Maybe. Okay. So don't get confused or lost. Fine. My dear students, thank you very much for attending the class.